Yes, thank you so much, and thank you, the organizers, for organizing this wonderful meeting at this wonderful institute and in this wonderful city. In particular, thanks to Tamar, who persisted in organizing this so a few years later. So yeah, and I hope I didn't have too much apple strudel for dessert last night, but it should be okay. I think John and I enjoyed it, and if you haven't tried it yet, so so, okay, this talk has two parts. The first part, which I'll probably go through rather quickly in the interest of time, is presenting a multi-scale coarse-grained modeling of nucleosome core particle phase separation from atomistic to mesoscale modeling. And the second part, which is in some way actually connected, as you will see, presents the columnar structure of telomeric chromatin and some new results on how sheltering components TRF1 and TRF2 interacts with the telomeric chromatin. So this work has been driven by Terry Sun, and these are the people that were working on this during several years, and the aim was to develop a coarse-grained model of the nucleosome and of the chromatin fiber. Yes, and as we see here, and presently we are working on this, but I will present the results of the coarse-grained modeling of the nucleosome core particle. And first we developed the DNA model, and it turned out to be very successful. It's a quite simple coarse-grained model, which is based on 5 beads per 2 base pairs, where the phosphates are explicit, and explicit ions in the coarse-grained system. And it's based on using the inverse Monte Carlo method to do a bottom-up coarse-grained modeling of the DNA in this case. And then we do a second step of coarse-graining and inverse Monte Carlo to get the effective potential for a super coarse-grained model to be able to model phase separation. And as seen in this slide here, here's the DNA, and so our aim to test this super coarse-grained model of DNA, which is based on atomistic simulation. I have to emphasize this, that the effective potentials that work between the beads in the super coarse-grained model of DNA, which is very simple, just connect the beads on a string for DNA. These effective potentials implicitly contain the effects of water and ions through the coarse-graining. Of course, it's known that long DNA, this has been known for many years, in the presence of multivalent cations like cobalt hexamine, will form this toroidal structure. So what we found is quite remarkably that this model, when we run the simulation, it indeed holds to a toroidal structure with hexagonal packing of the DNA. So we are quite confident that this DNA model is very good, and we went on to consider the coarse-grained model for the nucleosome core particle, which is indicated here. And the way we did this, because we wanted to make simulations of macroscopic phase separation of nucleosome core particles, for which there are several experiments. This in a way also validates the NCP model, which is going to be used later on in modeling the chromatin fiber. So the way we did it is that we extracted these effective potentials from subsystems rather than simulating a large number of nucleosome core particles and extracting the and then from these various subsystems, we get all the effective potentials for this coarse-grained nucleosome core particle model, which has the same DNA model at the coarse-grained level, as I presented in the previous slide for DNA. And then the The hysterectomy core is modeled with one amino acid, one bead for each amino acid. And with this coarse-grained model, you can put 20 NCPs in the presence of explicit magnesium or cobalt hexamine in the simulation box, and you find that the aggregates in the presence of multivalent ions. The nucleosomes stack on top of each other in these small columns. And one interesting part that you can analyze from this is the contribution of the tails to the stacking of nucleosomes on top of each other in these columns. And this is the analysis of the external tail spatial distribution function around the given central nucleosome. In other words, it shows the interaction of the neighboring tails with the central nucleosome, and it shows that the H2A exhibits the major part of this bridging interaction that facilitates the stacking of the nucleosomes on top of each other, together with H4. And largely this is related to how they exit on the DNA relative to the DNA gyres on the nucleosome, but H2 is instrumental in this. Okay, so moving on, having established this coarse-grained nucleosome core particle model, we went on to design a super coarse-grained model of the nucleosome core particle, modeled here. So it just has 9 beads, so 6 beads that are the same strands binding on the hysterectomy, plus 2 different beads here at the point. And from this model, of course, these are this is the effective potentials now, again, implicitly contain the effects of solvent and water, but since there are very few beads and you can easily model up to thousands and thousands of nucleosomes in the simulation system. So we went on to do that. So this is the super coarse-grained simulation of a system of 5,000 nucleosomes. And depending on this is in the presence of cobalt hexamine, which is known to induce various ordered phases of NCPs experimentally. And depending on the amount of cobalt hexamine in the simulation system, for the super coarse-grained simulation, in order to vary the concentration of the cation, in this case cobalt hexamine, you have to perform different coarse-grained simulation, extract potentials for that ion concentration, and then move on to super coarse-grained modeling. So depending on the concentration, you get different types of aggregation, and in a given range here, as you can see the formation of ordered phases. One very interesting aspect is the lamellar columnar phase. Actually, this has been seen, but not in the presence of cobalt hexamine experimentally, but under other conditions, the lamellar columnar phase. But we are very interested in this columnar hexagonal phase, which is well established experimentally. So at this concentration range or around it, the nucleosomes aggregate to an ordered hexagonal columnar phase. So the nucleosomes stack on top of each other in a hexagonal lattice. And of course, this is well known experimentally, this behavior. And the pioneer studying this was Vivo in Paris. And later we did a very systematic study of the effects of histone tails and so on the formation of this ordered nucleosome core particle phase. And the way you do it is that you do X-ray diffraction studies using small angle X-ray scattering beamline, and then you get these Bragg peaks which can be annotated and tells you what kind of phase you have and the distances between the nucleosomes in the columns and between them in the hexagonal phase. And so from the super coarse grain simulation trajectory, we can calculate the structure factor and predict the X-ray diffraction vector, which is shown here in red, which indeed actually is very similar to the experimentally determined X-ray diffraction spectrum. So it shows that this model can reproduce this macroscopic phase behavior, and of course the next step we are working on is to move on to model a chromatin fiber, and hopefully then we can learn something more, even more interesting. Okay, so I think this concludes the first part. I went through this very quickly, and if you have questions, just come back to me later. But the main point, of course, which is not new, but we showed here that we can model this, is that nucleosomes, mono-nucleosomes, they like to stack on top of each other through stacking interactions mediated by histone tails in the presence of multivalent ions like magnesium, cobalt-hexamine, and spermidine, and so on. And macroscopic phase that is formed is hexagonally ordered phase, which we can model and reproduce. Okay, so the next second part of the talk, I will talk about telomeric chromatin. So this work has been going on for some 10 years or more, actually. So, and it took a very long time. I mean, it took really a long time. There were many technical challenges, but it was part of a larger program led by Daniela Rose when she was in Singapore. And my group was interested in understanding and asking the question, what is the structure of the telomeric nucleosome and the telomeric chromatin? And of course, the telomere has unique DNA sequence. And in mammalians, it's comprised of TTAGGG, which is just repeated for 15 kilobase pair. And so there is no positioning information. And we hypothesized that this would lead to unusual structural behavior, but we didn't know anything about what we would discover, actually. So the first part of this, which was driven by Soman, a very talented postdoc, now having a semi-independent position. And so he determined the crystal structure of the telomeric nucleosome core. And somewhat surprisingly, it's very similar to other nucleosome core particle structures that have been determined both by Cryo-EM and X-ray. And there are many of them, but there are not many different DNA sequences. So that was perhaps a bit surprising. But when we looked at the properties of this nucleosome, the telomeric nucleosome, in solution, it turns out that it is significantly more mobile. This is shown by SAX data, solution SAX data, as well as NMR data that she was a postdoc with me at that time. She is now an associate professor. Yeah, so what we found is that this data showed clearly that the telomeric nucleosome is significantly more mobile than, say, a 6-to-1 or alpha satellite nucleosome. So the next step was to develop a method to reconstitute telomeric chromatin fibers. And it was not easy, and it took many years. Much of the success is due to these three people, in particular Simon Lackman, extremely talented staff scientist at NTU. And so he developed a method to do this in a controlled way. And it's very, very difficult because of the difficulty is to amplify repetitive sequences in a controlled way without deletion effects and so on. But we managed to develop a method that can do this in a controlled way, and we can reconstitute telomeric chromatin fibers. And under low salt buffer conditions, the fibers are somewhat heterogeneous in the nucleosome positioning, which is not surprising given there is no positioning information. And also compared to a 601 fiber, there are fewer number of nucleosomes. There is just much more heterogeneity in these fibers. But then we turned to, and again, this work was driven by Agil Soman. So he used the telomeric tetranucleosome in order to do single particle cryo-EM. Because we have observed that for longer fibers, we see these columnar elements, and we thought that using smaller fibers would, of course, give us more homogeneous and better resolution in cryo-EM. So this is the columnar structure that we then identified, and of course, this was quite surprising. I should go back here. Yeah, this is just to show the columnar structure. The resolution, the cryo-EM resolution of the tetranucleosome is not very high. It's something like 7 angstrom. But we did many data sets and different preparations, and the columnar structure is very much great. And it happens 80–90% of the fibers form this columnar structure. And we could analyze the dinucleosome unit of the tetranucleosome at much higher resolution, and this revealed different contributions of the histone tails, which I'm not going to talk in detail, but it's in the paper, and about it if you're interested. But the histone tails are of course crucial in mediating this columnar stacking of the nucleosomes in the telomeric chromatin fiber. But the details of this is very different compared to how the nucleosomes stack on top of each other and are mediated by histones in crystals or in the precipitated NCPs that I discussed previously. Okay, and we also noticed some other interesting features. In the data set, we could identify a 3D class that gave rise to this open state structure. And this is very interesting because it exposes the acidic patch, and this opens up the opportunity for and possibility for various chromatin factors. And of course, as you know, the majority of all chromatin binding factors, they bind to the acidic patch. So this dynamic opening of the nucleosome then suggests a possibility for telomere maintenance by various proteins like 36 and others that can bind to this. This, of course, remains to be seen. Another interesting feature is that actually this open state, they never say anything about it in Luger's paper, but it's they have a picture. But it was identified in archaeal chromatin, so suggesting that this is an evolutionary preserved feature. And interesting for the last part of the talk here is that you can also identify this supergroove feature on the columnar structure, where you have aligned grooves, which gives opportunity for various factor binding. Okay, I should move on. So, well, why columnar structure? Actually, why not? I think, given what I said in the beginning, and what we know, nucleosomes like to stack on top of each other. That's just natural, because it's like coins that stack on top of each other for packing considerations, and then in the presence of high salt that reduces the repulsion between DNA, and due to the mediation of the histone tails, this is what nucleosomes like to do if they are isolated. But of course, in positioning sequences like 177 and 187, chromatin fiber is almost forced into a zigzag structure, because it's the only way where it can achieve or a solenoid structure, but it can achieve stacking, and nucleosomes like to stack. So for a telomeric sequence where there's no positioning information and all the positions are isoenergetic, they would slide in the presence of salt, they compact, they would slide and arrange the fiber in this columnar form, which, when you think of it, is quite natural and perhaps not so surprising when you have the answer. Okay, so of course the telomere provides the protection of the ends of the chromosome, and crucial here is the sheltering complex, which is a complex of 6 proteins that provides the protective cap at the end of the chromosomes. There are 2 interesting proteins here, TRF1 and TRF2, telomeric repeat binding factor 2. And they have DNA binding domain, both of them, that recognizes the telomeric sequence. And then there's a homodimerization domain, and they differ only basically terminal part, which is, in one case is acidic and in the other is basic. So we wanted to investigate the interaction of these sheltering components with the telomeric chromatin fiber. And this work was done by Jacqueline Wong as well as with Soman. And what we found interesting is that, and these are results for the truncated version of TRF2 without the N terminal, but actually we showed that the same structural features is observed for the full length. So in the presence of TRF2, the columnar form of telomeric chromatin is induced without the presence of magnesium or other multivalent ions. And analyzing this, she found that nucleosomes are more tightly stacked compared to the magnesium-induced columnar structure, and the fiber width is also larger, which implies that TRF2 binds on the columnar structure and induces when it induces the columnar form. And this is just a hypothesis, but we propose that TRF2 can align over the supergroups and sort of connect 2 nucleosomes and bind quite strongly, which you can see in binding assays as well, that it binds strongly. And this is supported by single molecule magnetic twister data, and here I have to give credit to John. John was actually visiting prof to NTU in Singapore for more than 10 years. And when we had this grant, it financed the building of the magnetic tweezer that we had in NTU. And John, of course, helped us to build the tweezer. And every year he just upgraded it and made it better and better. And according to John, it's the best single molecule chromatin pulling tweezer in the world, even better than his own. But interestingly, when we pull on these fibers in the presence and in the absence of the TR2 protein, and I should say that for the telomeric fiber without this protein, the stretching curves, I think John will present this model that we can use to analyze these force extension curves. The data that we obtain in the absence of the protein, actually the features of the traces are very similar to, say, 601 or chromatin fibers. But in the presence of TRF2, the important parameters that describes the different stages in stretching the fiber and highlighted in particular the force constant and the 2 delta G that characterize the unbinding of the DNA from the histone octamer in the 2 stages in this model. And these parameters are highly different in the absence and in the presence of TRF2 protein. They almost double. So it shows that we get significantly more thicker fibers and they are thermodynamically more stable. And this is in quite stark contrast to the data for, I'm going to finish soon. The data that we just recently obtained for the TRF1 protein, and in negative stain EM, we don't see much of the columnar form being induced by the TRF1 protein. Instead, we see this cross-linking. And in the pooling data, there is basically no or very little effect on the protein on the mechanical and thermodynamic properties that characterize the fiber during stretching. So, yes, everything in vitro. Yeah, so the summary, and this is a model that we hypothesized, of course, is that TRF2 binds to supergroups and induces the columnar form, while TRF1, the component protein, can cross-link and bridge different fibers, and in this way they both sort of provide protection and maintenance of the heterochromatic form of the telomeric chromatin. And I didn't have time to show this data, but they have also shown that TRF1 and TRF2 induce liquid-liquid phase separation and droplets in different ways, which is model. These observations qualitatively fits in with the decrease in TRF1 and TRF2 expression and the phenotypes that are related to exposure to DNA damage. So with that, I come to the last slide, and this is the acknowledgement. Yeah, so these are the people that are presently working with me. Phasing out since I'm retiring. But a lot of people worked during the years in this telomeric chromatin and in the modeling project, and some of them are mentioned here. Collaborators at NTU, Daniela Rose, when she was working there, François Liu, who's a peptide chemist, Kurt Davey, who's now relocated to Switzerland and for the moment left academia, and Sarah Sardin, who is now a staff scientist at UMIO. And external collaborators, Chen Yangxi, and of course John Van Noort, who played an instrumental role in the tweezer work and enabling this. It's quite painstaking. We spent, again, many years to get the tweezer to work, but once it works, you get beautiful results. So here are the fibres in Singapore. And thanks for your attention.